Welcome to the new quantum era. I'm your host, Sebastian Hassinger. I'm recording this at the American Physical Society's Global Summit, a conference that brings together 14,000 physicists from all over the world. As you might imagine, quantum information and quantum computing are very hot topics at this event in 2025, so I was really excited when the opportunity arose to spend the week here recording interviews with some of the best-known researchers in the field and many new and upcoming talents. I want to thank the APS for providing me with space to record and to apologize to the social media teams I had to kick out of the room. I don't have the luxury as writers do of sharing space when I'm recording, and I apologize for that. Today's episode is with Will Oliver, and it was actually recorded the week before this summit due to scheduling conflicts. Will was suggested to me as a guest by the kind sponsor of this episode and of several more episodes upcoming that I'm recording this week, Quantum Machines. Quantum Machines OPX 1000 is tailored for large-scale quantum computers, offering unparalleled performance, scalability, and ready HPC integration, including an ultra-fast interface to GPU and CPU accelerators for boosting quantum control. With hundreds of deployments worldwide, Quantum Machines solutions are trusted by quantum computer builders, research labs, and HPC centers. For more information, visit quantum-machines.co. And with that, let's get to my interview with Professor Will Oliver. Welcome back to the podcast. We're joined today by Will Oliver, a professor of physics from MIT, who's been very deeply involved in quantum computing for a very long time. I think one of the OGs of the field in a lot of ways. MIT, of course, has been in. Ike Chung, I think, built the first ion trap at MIT back in the early 2000s, right? I mean, he sort of pivoted from NMR when he joined MIT. So the history of the university goes way, way back. But today we're going to talk about some stuff that Will's been leading and involved with Fluxonium Qubits. So a new variety of superconducting qubits that have been turning out some really impressive results. So welcome, Will, and thanks for joining us.
Yeah, thanks, Sebastian. I'm really glad to be here and looking forward to the discussion.
That's great. So we're probably most familiar with the Transmon sort of design of superconducting qubits. That's what IBM and others have been building for quite some time.
Yep.
I think Fluxonium also came, if I'm not mistaken, from Yale. I think it was Devray published a paper on Fluxonium sometime a few years back. But I think you at MIT are the only ones who are sort of really putting a lot of effort into improving the performance of those Fluxonium qubits, right?
Well, I wouldn't say that. I mean, you're right that we certainly are putting a lot of effort in, but I'd also, recognize my many colleagues around the world who are also trying to do that. And of course, Vlad Manacharian is one of them, and he was on the original paper with Michelle,
Okay.
who was a grad student there, and he's continuing to look at it. And there are a few other folks also doing it worldwide. But you're right, we're putting a lot of effort into it, primarily because it has a lot of nice features which we can talk about.
Yeah. Well, I mean, let's start with that. I mean, what differentiates the design of a Fluxonium qubit versus a Transmon?
Yeah, it's quite different. Actually, a Fluxonium's a lot like the old flux qubit, persistent current flux qubit that Hans Moy and Terry Orlando developed in the late 90s, in the sense that it's got a double well potential. As you know, the Transmon, its potential well looks a lot like a harmonic oscillator. It's only slightly anharmonic. But the Fluxonium looks a lot like a double well potential. It is. And so, like all flux qubits, it's a loop of superconducting material. and it's interrupted by one what's called black sheep junction or small Josephson junction, and the role of that junction is to let magnetic flux into or out of the loop. And then the rest of the loop is basically a large inductance, and that large inductance is realized by about 100 or so Josephson junctions. Now they're bigger. Those Josephson junctions, each one in area, is bigger than the small black sheep. So we just consider them basically as linear inductors. You put 100 of them in series, you have a pretty big inductance. And so that black sheep junction with the large inductor in a loop is what we call fluxonium.
Okay. And so it's controlled by microwave pulses the way a transmon is, right? So those pulses are then creating or modifying the induced charge on the fluxonium qubit.
Yeah, you can either drive it capacitively. I didn't mention this, but there is a shunt capacitor often added to that small junction. Originally there wasn't, but now we do that. So you can drive it that way, called charge driving. But you can also flux drive it. You can have a microwave antenna coupled to the qubit and modulate the magnetic field in the loop, and that's another way to drive it.
Okay. And how are you doing it at MIT?
We do it both ways. We do it
Okay.
both ways. We do charge driving and flux driving, and in fact, we've done a comparison between those two. I'm an old flux qubit guy, so I like to flux drive everything. But most of the students and postdocs in the group these days, they all grew up with the Transmon, and so everybody's a charge driver. And it's nice to have a bake-off once in a while and see.
That's interesting.
Yeah.
So the results you published in the MIT Technical Review, I think in January. I'm not sure when the original paper was published, but
Yeah.
it was covered in the magazine in January. The 1-qubit gate fidelity was nearly 5 nines, which is kind of extraordinary for a superconducting qubit.
Yeah, that was, we've been working for, along with the community for 20 years to make superconducting qubits better and better. And of course, coherence is part of that story. But what really matters for implementing algorithms, and the promise of quantum computing is to get high fidelity, right? That each operation works well. And so we actually had to go back to the drawing board and really dig into what's limiting the operational fidelity of these qubits, not just Fluxonium, but any qubit. But we did it with Fluxonium because it already started with a high coherence time. So, most fidelities in superconducting qubits, anyways, are nearly coherence limited, meaning if you make the coherence longer, the fidelity gets better. But we had already reached basically the coherence limit of Fluxonium. I should mention it's, some of the times that we see is T1 around 1 millisecond and T2 around 300 to 500 microseconds. And so starting there, the question was, can we reach the coherence limit in Fluxonium? And so that led us to, the techniques we developed in this paper to get it to 5 nines.
Wow, that's amazing. And was that using charge driving or flux driving?
Well, we did it with both. And in the end, the flux driving turned out to be a little bit better. And for two reasons, which we could go into in more detail if you'd like. But in a nutshell, we had coupled the charge line a little bit too strongly to the qubit. So we were driving it a little stronger than we would want to. And also a design aspect of the Fluxonium, or a feature of Fluxonium, you could say, is that the charge matrix elements are pretty strong all the way up the spectrum. And so you want to drive 0, 1, and you can do that pretty well because of the high anharmonicity of Fluxonium, but you still have a non-negligible leakage to the higher energy levels. And that leakage at the 5 nines level is, you can't ignore it. Yeah.
Right. Interesting. And you said you also, that was a 1-qubit gate, but you've got quite high fidelities on 2-qubit gates as well subsequently, right?
Yeah, well, actually, we started with the 2-qubit gate. So this device has 2 qubits, 2 Fluxonium qubits, and we used a transmon as a coupler between them. So we could basically turn on and off the interaction. And in that gate, and this was by Leon Ding, who graduated in 2023 with his PhD. So he led that effort, and he was able to get 99.92 to 3, something like that, on this gate over several hours. So that was the device, and then the follow-on work was, okay, well, let's look at the single qubits and see how good we could do. So then Leon and also David Rower, who led this effort, recently graduated as well, um, looked at the single fluxoniums and then did this experiment to get almost 5 nines.
Wow, that's cool. And so like you're talking about a test device, an experimental qubit device with just a couple of qubits on it. Is there like how do you think the design of Fluxonium will lend itself to larger scale QPUs?
Yeah. So the one thing about fluxonium is that it's somewhat sensitive to capacitance, and in a sense, there's a capacitance budget that one has to respect. Now, because of that, I think at a cursory level, people decided, oh, Fluxonium, it's interesting at the 1 or 2 qubit level, but it'll never scale because of this capacitance limitation that you have. We worked through it, came up with some designs such that we can actually couple them in a north, south, east, west manner. So you could make a surface code out of this. I think that, um, you know, there is a regime of parameter space in which Fluxonium will scale. And that turned out to be the genesis of a startup company that came out of our group called Atlantic Quantum. Yeah. So we certainly did our homework before launching that
Yeah,
company.
I assumed so. Yeah, 1 qubit's not going to get you very far.
No, that's right.
Recent press releases notwithstanding, but
0 qubit.
yeah, yeah. So Atlantic Quantum is the name of the startup. I think it's still sort of in development mode, right? I haven't seen any launch plans or anything of a device, but
That's
you
right.
must be sort of heading in that direction. You've got sort of a plan to get something into the hands of potential customers.
Yeah, that's right. So we did our seed round almost 3 years ago, I think early 2022. Um, 13 million raised, and then we got about that much again in non-dilutive government funding. So this year we're starting an A raise, but right now the main product is IP and how one can build a scalable Fluxonium-based quantum computer with a focus on driving down the cost per qubit. That's the main feature. Turns out Fluxonium has a rather low frequency compared to most qubits. You can operate at around 100 megahertz, 200 megahertz, whereas typical transmons might be around 5 gigahertz. That low frequency turns out to have some very, very nice features, and that's where our IP is really centered in terms of how you can control it in somewhat non-standard ways, but ways in which you can co-locate cryogenic electronics and thereby reduce the cost per qubit substantially. So anyways, that's the direction that Atlantic Quantum's going.
That's really cool. So you're saying essentially a lot of with transmons, you've got to operate, as you said, sort of in the 5 gigahertz
Yeah,
range,
that's right.
and that means you've got to put a microwave lead down in the dill fridge for every qubit. At this point, we haven't figured out how to multiplex, as far as I know.
That's right.
Um, yeah, and so that's a huge space constraint on what you can fit in a dill fridge, and also, as you said, it's very expensive. On a per qubit basis for the control architecture. So you think Fluxonium would actually be able to have some of the controls actually in the fridge with the qubits?
Yep, we do,
Huh.
and that's really what Atlantic's focused on right now. And you can drive down the cost a lot because, as you just said, right, a 5 gigahertz generator is pretty expensive, burns a lot of power. It's basically a little computer at room temperature, right? It's got an IC inside. Once you reduce the frequency dramatically, then that opens up a lot of new doors that you can, start thinking about putting a lot of this stuff down at cryogenic temperatures.
Interesting. That's really cool. So that potentially would mean you'd be able to fit more qubits in a single dill fridge as well, because you wouldn't have to have one of those big leads all the way from room temp down to the millikelvin range.
Yeah, that's
That's
exactly
really
right.
great.
Yep, that's exactly
So
right.
are you building your own sort of control stack as well then, because of the sort of the unique characteristics that you're designing around?
We do have teams of people now that are focused on what that control looks like, both in terms of design and emulation of the signals, testing those
Hmm.
signals, and designing the cryogenic electronics as well.
That's really cool. That's really cool. So then what I mean, can you sort of project the sort of whatever the target for how many qubits you might be able to fit in a single dill fridge with this type of setup?
Yeah, it's hard to say because there's so many different types of dill fridges, and really, if you needed more power, you just would make add another mixing chamber and make it twice as big, and you've got twice as much cooling power. So I'm hesitant to say, a concrete number, but I can say with certainty that it's a lot more than what we're currently doing with all those coaxes coming down.
Right, right.
Yeah,
Yeah,
yeah.
that stands to
There's
reason.
a big win per qubit, and the more you can do it, you think about it, right? Today we're probably close to five or even $10,000 per
Yeah,
qubit, and
that's
we
the
know we're
number I
going to need
usually
millions of
hear.
qubits.
Yeah.
How many of those computers can we really build?
I know. I know the math starts to get pretty daunting when you start multiplying by, like surface code ratios and the number of logical qubits you need for something like Shor's. It starts sounding like a very, very expensive computer indeed.
Indeed, indeed.
Um, so that's really cool. So you mentioned surface code? Is that sort of what the play is then? Is to build a chip at scale that can implement surface code for error correction and produce sort of logical qubits out of those. I mean, obviously, because the fidelity is so high, your ratio is actually going to be quite attractive, right? Of physical qubits to logical qubits.
Yeah, that's right. So we're part Atlantic Quantum as well as MIT campus is part of the IARPA Entangled Logical Qubits program, or ELQ as it's called. And so our goal there is to do one and two, ultimately 2 qubit gate operations, and we'll do that with the surface code. Fluxonium's in a surface code architecture, and this is really, it's a great platform because we know we're going to need error correction, right? I think, the community's been trying for a long time to come up with something in the NISQ era that's useful, and we still may find it. I'm not going to say it's not going to happen. But if you take a step back and say, okay, what's really going to take us to commercial value and realizing that commercial promise, it almost certainly is going to be an error corrected machine just because of the depth of
Yeah,
the algorithm that we require. And so we're focused on, improving the fidelity of each qubit and then scaling up. So make better qubits and then scale them up. And, starting with surface codes and error correction is a great idea. I do have, some students at MIT who are thinking about QLDPC codes, so quantum low density parity check codes, and long range couplers and things like that. And when those types of elements become real, then companies can adopt them and try other codes. But right now, the surface code matches the nearest neighbor connectivity that we get in a superconducting processor quite well. Yeah.
yeah, yeah. Yeah, and I mean Google's result from the end of last year, of sort of the below threshold, was really, I mean, it was such an incredible step. Unfortunately, often misconstrued in the popular press.
Yeah.
But that's kind of, I mean, that's one of the motivations for this podcast is to try to add a little bit more nuance to this to the news. But I mean, effectively they proved that the surface code is an efficient way to, and like the more physical qubits you add, the longer you can actually operate in a fault tolerant mode.
Yeah.
And it was definitely good validation for people like yourself who are planning on implementing surface code.
Yeah.
Is there, when you think about the way you're going to lay out the chip, like you said, nearest neighbor, the sort of the laid out in a cross, right, like a lattice. So
Yeah.
you've
That's
got
right. That's right.
north, south, east, west. Do you is there any major difference in the way that you're going to have to implement surface code compared to the Google approach? Because I think that was a lattice as well, right?
That's right. Yeah, that by the way, the Google result was really fantastic, and so glad to see that. I mean, it was the first time on any platform that this had been experimentally shown, and this is the side of the line we got to be on. So good to see. Um, I think there of course will be differences in the details, but I think this general pattern of a lattice of qubits and coupling north, south, east, and west, that this is what it will look like. Yeah, that's
Right,
right.
right.
Yeah,
That's really cool. And so, do you, you mentioned other approaches that are being experimented with by other groups within MIT. Is
sure.
it feels like this we're still in this stage where it's like we should be exploring all the possibilities because no one can sort of claim to have a clear path. Are there other potential modalities that you're also interested in?
Absolutely. So even in our own group, we've got currently 12 DIL fridges, but two of them are for semiconductor qubits. So we're working with Intel and HRL, and what we can bring to semiconductor qubits is perhaps what we've learned from superconducting, like superconducting couplers or something like that. A lot of 3D integration work that we've done, and trying to understand, what parts of that can be brought to bear for semiconductors to help out that modality. But semiconductor qubits are really starting to stand up in the last few years, and lots of fantastic progress, for all different types. There's so many different types, even.
Yeah,
Yeah.
it's true. It's sort of opening an entirely new can of worms in terms of the diversity. I mean, so is it? You mentioned Intel, so this is in conjunction. What was it? Tunnel top? Is that what they called their chip? I think something. They had a 12 qubit
Yeah, that's
experimental
the one. So 12 qubits in a
spin
line.
qubit chip. Yeah.
And what's nice about that, I really like that design because you could operate each one as 12 single qubits, or you could do six double dots, or you could do four triple dots, right? And so, you could really test all of these different modalities against one another with the same, fundamental qubit design, which I find to be pretty interesting. And yeah, so that's one of them, and this is enabled through the LPS Foundry program. Also with HRL, also part of the LPS Foundry program, looking at their version of triple dots specifically. So we're just starting. We don't have any major results yet, but um, we are dipping our toes in semiconductor qubits because I think like we just said, they're starting to stand up, and it's pretty
Yeah.
interesting.
Well, and certainly, I mean, intuitively, it feels like if you can crack the code on doing quantum dots or spin qubits in silicon, then you certainly have the know-how for doing silicon at scale. Like
Yeah, well, that's
all of
right.
a sudden it becomes like the scaling question sort of becomes easier, I think. I mean, at least that's what I would imagine.
Well, and I think you hit the nail on the head in the sense that all of these platforms have superpowers or strengths, and they also have weaknesses, right? And so clearly, semiconductor qubits have that superpower, which is that if you can make them in the foundries which already exist, you've already got a leg up on scalability, And superconducting qubits, I would say, also fall in that camp, and even photonic qubits, right? A lot of the integrated photonics can be made in these. So it's not just the domain of semiconductor qubits, but of course, on the other hand, they are indeed the closest to that. And the 3D integration that we're going to require to in any of these platforms, of course, has been developed quite extensively for semiconductor chips and chiplets, and we're seeing it more and more as we've gotten beyond Moore's law. It doesn't mean it's the end of the roadmap. It just means, okay, instead of making the chips faster, we're just going to 3D integrate them more and
Right.
more. Yeah.
Right. That's really interesting. And I think MIT is part of the C2QA, right? The DOE NQI Center.
Yeah, we're part of the Brookhaven one,
Right.
and we're also part of the Berkeley Sandia one called
Oh,
QSA.
cool.
So
Right.
C2QA
QSA.
and QSA, we're members of both of those.
Right. I was just curious because C2QA sort of has the co-design kind of ethos sort of embedded in its mission, meaning like sort of algorithmic design or experimentation, sort of interacting more with experimental approaches to qubits and architectures. Has there been any of that sort of interplay between sort of the theorists and the experimentalists in the work you've done with the Fluxonium?
Yes, there has been. We've talked with folks at C2QA and theorists there about experiments that we could do with Fluxonium, also with transmons, and that turns out, it's a big part of that program as well. And then, to be fair to QSA as well, co-design is a big part of that one, and also the theorists in the QSA team. So, but there it's less focused on. For both of these centers, it's less focused on I'm going to use Fluxonium and not Transmon, or Transmon and not Fluxonium. It's more about what can we achieve and what's the best qubit to achieve a particular goal, and that's a derivative of this co-design mentality.
Right, right.
Yeah.
That's really interesting. Yeah, it does feel like there may be some kind of interim stage where we have multiple modalities in single system architectures that leverage, as you said, the superpowers and try to make up for the weaknesses of each of these modalities when you look at them one at a time.
Yeah,
Do you,
sure.
I mean, is there that kind of integrated architecture thinking happening at all at MIT with all the different modalities you've got in play?
Well, I would say that within, say, the cryogenic ones like superconductors and semiconductors, that is an area we're exploring, and we don't know yet if it's going to pay off in the end, because there's no free lunch. We gain some of the superpower, but we also gain some of the some of the part that's not so good, and so which one wins in the end, we'll have to see. um, of course, MIT is also doing trapped ions, neutral atoms, some photonics work. We haven't really tried to, say, combine yet superconductors and, say, the natural atoms, mostly because the time scales are so different. And usually you're limited by the slower time scale, which means, by the time the superconducting qubit can give its information over to a trapped ion, it's already lost the information, because superconductors are fast and they lose their information fast. So,
Yeah.
yeah,
I
if we
guess,
could
I mean,
speed up.
I just wonder from a certain perspective that slowness and long coherence times on atoms almost looks like, storage, like to a superconducting qubit.
It does, and people have suggested this, and I'm definitely open to that idea. The roadblock that I keep hitting, at least mentally, as I do a mental experiment, is that you've got a fast processor of superconducting qubits, and then you want to put something into memory in a trapped ion, and the ions are about 1,000 times slower.
Right.
And so as the superconductors try to give that quantum information over to the trapped ion, they lose it before the trapped ion can get it. So then you say, well, let's make faster trapped ions. That'll work. But then if you can make them fast as the superconductors, just use the trapped ions. They're really good. So
Good point. Good point. I didn't think of that. Of course, it's the data input and output would be the gating factor.
yeah. So, but again, I think it's good to think through these things, and because engineers are clever, I will almost never say that something won't work. I
Right.
can only say what I'm currently thinking and why I have this mental block on it right now. But it's possible, right?
Yeah.
Let's keep chewing on it.
That's what I find so fascinating about this whole space is that this hardware is being developed like in this sort of knife's edge balance between applied science, like fundamental research, and really, really cutting edge engineering. It's an incredible sort of like the peak of both of those kind of um, disciplines and skill sets working in conjunction is something to see.
Yeah, yeah, no, you're absolutely right. And, probably for the first 10 or 20 years of this development, it was a lot of quantum science. And that needs to continue. But the quantum engineering, as we call it now, that needs to stand up. And I think over the last few years, a lot more attention's been given to it. But, we still need to, as an engineering discipline, develop the abstractions that allow us to then go forward and engineer quantum systems. And I think writing the textbooks, developing the classes, the courses that that people can take, the professional development courses. These are things that we're focused on at MIT because a, that's our job. We're supposed to do that, but b, it's going to be so important for the future. And the idea that we're going to build a large scale quantum computer at a university is kind of it's let me say it's probably not going to happen. That's the job of a university, that's the job of industry. Yeah, but what a university can do is, the fundamental basic engineering and the principles and learning how to scale, and then industry can take that learning and then apply it to actually scale. Yeah.
Excellent. Yeah, and hopefully, Atlantic Quantum can be an example of exactly that kind of handoff of the fundamentals, the roots of the learnings from the university lab into creating a commercial product.
Yeah, that's certainly the idea.
Yeah, that's great. Well, thank you so much for joining us, Phil. This has been really, really interesting. I look forward to reading more about Fluxonium and Atlantic Quantum, and of course, all of the incredible work that's going on at MIT. So thank you.
Yeah. Thank you, Sebastian. Really enjoyed it. Take care.
Thank you to Professor Will Oliver. Thanks to Quantum Machines for their support. Stay tuned for more from the 2025 Global Summit, and thanks to APS for their generosity. If you have questions or comments, follow the show on Blue Sky at New Quantum Era and reply to this episode's post. To find prior episodes, show notes, and transcripts, or to preview the book I'm writing on the topic, go to newquantumera.com. Thank you for listening, and if you want to support the show, please tell your friends. And if you have suggestions for topics or guests, please let me know on Blue Sky. Thanks again.